Today's lesson is going to be on ASA and AAS. So if you know that two angles in the included side of one triangle are congruent to the two angles in the included side of another triangle, then you can always prove those triangles congruent by ASA. So in other words, if you know that angle B and angle E are congruent angles, and you know that C and angle F are congruent angles. If we're looking for an ASA, then we actually want the side that's sandwiched in between the two angles. So then we can say, and BC is congruent to EF, then you know that triangle ABC is congruent to triangle DEF by ASA. So here's your first proof. Given that AC bisects BCD and CA bisects BAD, prove that angle B and angle D are congruent. The first thing you need to realize is what triangles do they want you to prove congruent? And hopefully you see that they're looking for this triangle, BAC, and this particular triangle, CAD. So let's see what we know. The first thing they tell you is AC bisects angle BCD, which means BCD, or the vertex at C, is what's being cut in half. So BCD would be this side, the inside of the triangles. So number one is given. And by definition of an angle bisector, we can now say that angle BCA is in fact congruent to angle DCA. Well, it also talks about how angle BAD is bisected by CA. So that would be your third statement, which is CA bisects angle BAD. That's given. Well, angle BAD is the vertex angle at A, which means these two smaller angles are now congruent. And that's also by definition of an angle bisector. So we're going to call it angle BAC is congruent to angle DAC. And this is also definition of an angle bisector. Well, we ran out of givens to use. There's nothing left. So what do you know for sure? Well, hopefully you see that there is a shared side. There's a reflexive side. So that's what I'm going to write next. And then I'm going to put line segment CA is congruent to itself. This is by the reflexive property. Now we have the three pieces of information that we need. So we can now name our congruent triangles. And I'm going to call one of them ABC, which is the top one. And if I call the top ABC, I must call the bottom ADC. And that side is sandwiched in between the two angles, ASA. And it's having us prove congruent parts. So that means angle B must be congruent to angle D. And that's because corresponding parts of congruent triangles are congruent. Okay, so there's your proof. Okay, so let's take a look at the next slide. If you know that two angles and a side that's not included of one triangle are congruent to the corresponding two angles inside of another triangle, then you can prove those two triangles congruent by AAS. Understanding that AAS is the same exact theorem as SAA. It doesn't matter how you write it, but just understand that the side is not sandwiched in between the two angles. So let's say you know that angle B and angle E are congruent. And let's say you know that C and F are congruent. Well, if we pick a side that's not sandwiched in between the two, we can look for this side right here, that BA and ED. So we can look for BA and ED, and then we can say, all right, these two triangles, if I call the first one triangle ABC, The second one has to be called triangle DEF, and this is by angle side. Let's take a look at the proof. You're given parallel lines, AB and ED. You're given angle B and angle D are congruent, and BC and DF are congruent. And you're asked to prove parts. So if you're asked to prove parts, we got to find those triangles first. So let's see what we can do with this first given, which says that line segment AB is parallel to line segment ED. So if I were to highlight those, this line segment and this line segment are parallel. Well, there's only one transversal that connects those two parallel lines together, and that would be this transversal right here. Well, parallel lines give you lots of different types of angles, but you tend to really just deal with alternate interior angles at this point. The alternate interior angles have to touch both the parallel line and the transversal. So the alternate interior angles here would be up here at angle A and over here at angle E. They might look like they're right angles, but you don't know that for sure. So here's what you're going to have to write for step 2. Angle, and we can just call it angle A because there's no confusion. There's only one angle there. Angle E and angle A are congruent. This should be number 1, by the way. And the reason is parallel lines form congruent alternate interior angles. Okay, there's no other transversal to use. There's no other pair of AIAs to use. We are done with that parallel line piece. Let's go back to the proof. What else is given to you? You are given that angle B is congruent to angle D. B and D are congruent. You're given that line segment BC is congruent to line segment DF. Oh, I forgot my givens on there, sorry. So 3 should be given, 4 should be given. So BC, which happens to be this guy, and then DF happens to be this guy. So now you have enough information to prove the triangle's congruent, and you've got the side that's not sandwiched in between the two angles. So I'm going to name my congruent triangles. I'm going to call the first one ABC. So therefore, I must call the second one EDF. And this is by angle side. Well, now once we've got the congruent triangles, and any set of corresponding parts must be congruent. So now we know that line segment CA and line segment FE have to be congruent because corresponding parts of congruent triangles must always be congruent. Let's look at the picture with it. Does it show the picture? No, it doesn't show the picture. Okay. Next proof. They're trying to have you prove RTQ and STP. So we don't need corresponding parts of congruent triangles, we just need congruent triangles in general. So let's see what we got going on here. So the first thing that they tell you is line segment RQ is congruent to line segment SP. And that's given, which is this to this. Then they tell you those exact same two line segments are parallel. So that's also given. Well, parallel lines always form lots of different angles, but the ones that we're probably going to be dealing with are alternate interior angles. We have 2 sets of transversals here, and we can use them both or not. I'm going to go for this transversal, and I'm going to say, well, it's very obvious that in between these guys, the hinged angles, in between the parallel line and the transversal, that's an AIA. But you know what? I could also, and there's no reason to not do this on the same line, if I wanted to look at this guy as a transversal, wouldn't you have to say that these angles right here are also congruent alternate interior angles? You do, in fact, as well have a pair of vertical angles, which you can use or not. I'm going to choose to not use the vertical angles here just because I'm not. We did it in class. We used the vertical angles for some of the classes. For some we didn't. But what I'm going to say next is I'm going to put two things on one line because it's all the same stuff. So angle R is in fact congruent to angle S, as well as angle P, it's supposed to be an R, is congruent to angle Q. And these are all from the same reason. Parallel lines form congruent alternate interior angles. Well, that's two pieces. Oh, no, that's all three, as a matter of fact. I'm sorry, that's all three. These were two for sure, but that was a third. You have enough information to prove these triangles congruent. In this case, triangle RTQ is congruent to triangle STP, and this is because of angle side angle. Now just understand something, okay? Let's say you only chose one pair of AIAs, not a big deal. And let's say you wanted to go for the vertical angles. If you chose vertical angles and one of those pairs of AIAs, you would have the same proof, but your final reason would be an AAS proof, not an ASA proof. It doesn't matter how you do it. It's whatever you see. Okay, let's go for the last classwork proof. Last one is this. They're telling you that you have RT line segment is perpendicular to TS, and they're telling you you've got RW is perpendicular to WS. Notice where these line segments go, that these guys at T, those are going to have to be a right angle, and these guys at W, those are going to have to be a right angle. If you want to incorporate those two together, that's fine. If you want to make them separate, that's fine. It's your choice. I'm going to go together, and I'm going to say that RT is perpendicular to TS, and the same line, I'm going to say RW is perpendicular to WS. I'm doing them on the same line because these are giving me the same angles. Well, let me rephrase that. They're giving me two different angles, but both right angles. So right from here, I'm going to say angle W, and watch what I'm going to do. Angle W is congruent to angle T. And my reason is going to be this. Perpendicular lines form congruent right angles. We have done it in class where we've done separates, and we said first given RT is perpendicular to TS, which makes angle W a right angle. And then you could say RW is perpendicular to WS, which makes angle W a right angle. You would still have to go one step further and say that W angle, angle W, and angle T are congruent because all right angles are congruent. That's an extra step. Again, it's your choice of how you want to set it up. Neither are wrong. Let's keep going back to the givens. We have angle 1 congruent to angle 2, and that is given to you. That happens to be a second angle. I'm going to bring this up a little bit. We're done with the givens. There's nothing left that they have told us, but hopefully you see that you have a shared side. So I'm going to say that line segment RS is congruent to line segment RS. This is by reflexive. There's enough information to prove triangles congruent because now we have a side that is not sandwiched in between. I'm going to bring this up a little bit, and I'm going to name my triangles. I'm going to go for the names of triangle RWS, congruent to triangle RTS. And again, we said that it was the side not sandwiched. So this is SAA. Remember, SAA is the same thing as AAS. And now that we've got congruent triangles, we can go to our proof statement. Now we know for sure that line segment RW must be congruent to line segment RT because corresponding parts of congruent triangles are congruent. Okay, and there's your proof. So that should be good to get you through the homework. Good luck.